Okay, thank you for your introduction. Hello, my name is Seunghee from KAIST, South Korea. First of all, thank you all guys to staying until the final session of the conference. I truly believe that you guys are here because you're interested, so I'll do my best to worth your time. Today, I will present our work titled LightNobel, Improving Sequence Length Limitation in Protein Structure Prediction Model via Adaptive Activation Quantization. As a brief overview of this presentation, in this work, we address the scalability limitation of protein structure prediction model, such as AlphaFold, which recognized with the Nobel Prize in Chemistry last year, while also accelerating them. Let me start the presentation. Okay, let's start with proteins. Proteins are everywhere around our life. From skins and hairs to hormones and enzymes, they are fundamental in nearly every biological function. To understand how biological system works, we must first understand the structure. However, this is not a simple task. Even though proteins are a linear sequence of amino acids, they fold into complex 3D structure shapes called tertiary structure. This structure determines the protein's functionality. In details, this 3D folding structure determines how proteins interact. They bind selectively only to others with compatible shapes. Hence, finding out protein structure is critical for biological functions related to biotechnology and pharmaceutical applications. However, experimentally figuring out the protein's 3D structure is slow and expensive, yet over 200 million are estimated to exist. To address this problem, recent advances have turned to prediction with AI-based models. Some models like Google's AlphaFold and Meta's ESM4 are examples of these models, and they have achieved remarkable accuracy. Last year, their impact was recognized with the Nobel Prize in Chemistry, so that's why we named our work LightNobel, light from lightweight and Nobel from Nobel Prize. These prediction models are called Protein Structure Prediction Model, in short, PPM. PPM predicts the protein's 3D folding structure, as I told you, from amino acid sequence. It's composed of 4 major parts. First, the input embedding stage prepares the related features of input protein from database. Then, the protein folding block stage updates the interaction and positional relationship between amino acids through attention layers. Next, the structure module stage predicts the 3D structure based on these updated relationships. And finally, the recycling stage repeats the same processes for more accurate prediction. Among these stages, the protein folding block, which includes the attention layer, is the key part of PPM. It introduces 2 new data structures named pair representation and sequence representation. Here, pair representation has 1 more dimension compared to activations in typical attention models. It creates a significant burden with increasing sequence length. Here, let me call the data flow that deal with pair representation data structure as pair representation data flow. Now I'll explain the key motivations of our work. First, we began with latency analysis. As a result, we found that as the sequence length increases, the share of pair representation data flow also increases. This is primarily due to triangular attention, which increases from 29% to 76% in this case. For very long proteins, this pair representation data flow is expected to occupy over 99% of our total workload, resulting in a scalability limitation. Alongside this, we also observed that the size of intermediate activation explodes. Because pair representation has 1 more dimension, as I told you before, its size scales quadratically with sequence length. Even for sequences around 2,000 amino acids, the activation size already exceeds the capacity of state-of-the-art GPU, such as H200. However, recent research says that some real-world proteins are longer than 40,000 lengths, which indicates more serious scalability challenge. So we turned to quantization as a fundamental solution. At this point, if we take another look at the graph, we can see that while activation size grows really rapidly with the signal's length, the weight size remains constant. In fact, ppm has a relatively small hidden dimension, so the weight size is significantly smaller compared to the activations. At a sequence length of 10,000, the activation size is already over 2,600 times larger than the weight size. So in quantization, the most important thing is to avoid accuracy degradation, especially for biological methods like ppm. To that end, from this observation, we choose not to quantize the relatively small weights and instead focus on the quantization of the activations. This allows us to fully leverage the benefits of quantization while minimizing any potential loss in accuracy. But even when using activation-only quantization, preserving accuracy remains a significant challenge. To achieve this, a new approach tailored to the characteristic of activation is required. During our analysis of activations to determine an appropriate quantization scheme, we identified two key characteristics. First, we identified histogram pattern across activation channels, as you can see in this slide. Here, the small variance between channels can be an opportunity for token-wise quantization. Second, we found that the activations have different distribution characteristics depending on their position. It demonstrates the requirement of activation adaptive quantization. So based on these insights, we propose a new novel quantization scheme named token-wise activation adaptive quantization, or AAQ. Let me first explain the baseline of our quantization scheme. We adopt uniform, symmetric, token-wise quantization as a baseline. To clarify, we define a token as a vector along the hidden dimension in the activation. Within this token, we separate inliers and outliers and handle separately. The quantized tokens are then formatted and stored efficiently, aligning with the memory bandwidth. In more details, we divide activations into three groups, group A, B, and C, based on tensor-wise value distribution. And then we apply different quantization schemes to each. We dynamically apply low precision for inliers and adjust the number of handling outliers depending on their characteristics. We also conducted design space exploration to find the optimal quantization scheme for each group. By prioritizing minimal accuracy drop, we identified optimal settings across all groups. Now, let's look at the hardware architecture. LightNobel is a hardware accelerator designed to efficiently run PPMs with our proposed AAQ method. It maximizes token-level parallelism and minimizes memory access overhead. Including the showing modules, it is built upon two main modules, the reconfigurable matrix processing unit, in short RMPU, and the versatile vector processing unit, in short VVPU. Okay, let's start with the RMPU. The RMPU is specialized in matrix-related operations and provides reconfigurable data flow to support multi-precision and various quantization token formats while maximizing resource utilization. RMPU has hierarchical structure according to operation level. At the lowest level, it has PE, the fundamental computation module. To support multi-precision operation, RMPU slices the operand data into minimal subunits and perform multiplication independently. Then, using shifters and adder tree, the result of each can be accumulated to produce the correct computation result. For example, assume the multiplication between two 8-bit data. Since the minimal subunit of the RMPU is 4-bit, 8-bit data is divided into two 4-bit data segments. 4 partial multiplications are carried out, and then shift operation and accumulation are performed. To preserve the original data signness, a 1-bit sign bit is additionally used for each segment. This architecture is the key element that allows the RMPU to support multi-precision computation efficiently. The group of 8 P's form a PE lane which supports multiple data flow. P cluster consists of 20 P lanes and a DAL to support token level operations. Here, DAL, or dynamic accumulation logic, plays the critical role in supporting various quantization schemes. Depending on the precision of inliers and the numbers of outliers, the computational workload can be vary even for a single token. Since the hardware resources are fixed, failing to account for this variation can lead to underutilization. To address this, DAL dynamically adjusts the token throughput based on the quantization schemes to maximize utilization of resource. More specifically, in our system, each DAL dynamically controls the token level parallelism between 4 tokens and 5 tokens, depending on the workload. Finally, our MPU engine consists of 4 P clusters at the top level and processes up to 20 tokens in parallel. Next, the VBPU is specialized in vector-related operations such as layer normalization, softmax, dynamic top K, and quantization. It features multiple SIMD lanes and a crossbar network for flexible data formatting and efficient scheduling. As in AAQ, we also performed design specs exploration for hardware configuration. The optimal configuration was found to be 32 RMPUs, each paired with 4 VBPUs, achieving the best performance resource balance. Now let's move on to evaluation. Evaluation is conducted using a cycle accuracy simulator. In accuracy evaluation, AAQ achieves less than 0.001 drop in TM score, which is an evaluation metric for protein 3D structure, and it is negligible. Compared to other state-of-the-art quantization methods, AAQ preserves accuracy more efficiently. For end-to-end performance, LightNobel achieves up to 141.3 times speedup over existing PPMs on recent NVIDIA H100 GPU. We also compare LightNobel against recent GPUs for the protein folding block specifically. LightNobel achieves up to 8.4 times speedup, and even when excluding the chunk option on GPU, which improves the performance but limits scalability, it still remains 1.2 times speedup. This shows that LightNobel provides most both performance and scalability benefits. As detailed analysis on the performance gain, LightNobel achieves up to 120 times lower peak memory requirement, 43.4 times lower computational cost, and 74 times 1 times lower memory footprint compared to conventional systems. This is the area and power analysis of our system, synthesized in TSMC 20 nanometer technology. They are mainly dominated by crossbar networks and the RMPU engine, which are key modules for AAQ support. Compared to recent GPUs, LightNobel achieves up to 43.9 times higher power efficiency. In conclusion, we propose token-wise adaptive activation quantization, AAQ, to overcome scalability limitation in PPM. Also, we propose a hardware-software co-design accelerator architecture with specialized RMPU and VBPU engines. As a result, our system shows up to 141 times speedup and 43 times higher power efficiency compared to recent GPUs with 120 times lower memory requirement and negligible accuracy loss. This is the end of my presentation. Thank you for listening. If you enjoyed the talk, please take a look at our paper for more details, and I'm happy to answer any questions. Thank you.
Thank you.